Yeah, we are recording.
Yeah.
Go ahead.
So as you can figure out with the white I have in my beard and in my head, so I've been around for a while. Started my career in 1998. It's very funny. I think I would have told you when we like maybe in our third or fourth discussion, like in the place that we were working, like both all of us together. It was very interesting to see that although we were on these embedded projects, but still it was not that well understood a domain.
Right.
But or we used to talk about it in a different vocabulary, and so it was very nice to see some of you like really uh, excited and motivated to explore more. So that was like I was like, okay, I'm at the right place. I'm not
Right.
so that was beautiful. But the reason I'm saying that is that when I started my career, for some reason I knew this was in 1998 that what I wanted to explore because of my internships. So I did my internships at CDOT Center for Development of Telematics, and in those days, they were just trying to get some of the 8-bit micros and some PLDs together and make these large boards for a switching system. And so it was like a kid in a candy store kind of a scenario for me, like so much to explore, so much. So I just had it in my mind that I wanted to write device drivers because they were fun, because the person who used to write for us in C dot could wiggle any LED when he wanted. And that was just so super exciting for me. Like
Yes.
I wanted to explore that more. So like I had that in my mind, and that sort of defined what I wanted to do. My first job, what I picked up, went to the industry consultancy and research center in IIT Madras. So I spent about 6.5 years in that setup. Was a part of an early startup there in the campus, Midas Communications. That was a part of these companies that mushroomed over there. Now they've moved to the Taramani Research Center, but they just came up in the campus at that time.
Right.
Um, that sort of gave me a lot of insights into how these systems are built. We never distinguished between hardware engineering and firmware in those days. Like it all was like you debug using very basic tools, and every engineer, software or hardware, would know soldering. The passives were large enough that you can see them and solder.
Right.
Yeah. So yeah, that was very exciting. Then I moved to Texas Instruments, stayed there for about like 17 plus years.
This was which year when you made the
So I moved
shift?
to Texas Instruments in 2004.
I
So
see.
from 1998 to 2004, I was in this IIT Madras and the
Madras
companies that
campus.
were
Right.
um, then moved to TI, and TI 17 years. Practically every few years, you discover a completely new product line, a completely new technology. The foundation was still like embedded systems, firmware, but different applications. TI gave me a, a lot of space to explore, and I met really smart people over there, learned a lot, had a chance to create some really good products. Moved to Google in 2021, and
Right.
um, again, a very talented team, something which was coming together. It was so nice to see the whole team coming together. If I remember,
Yeah.
like when we came back from COVID, like
Yes.
it's such a small team, like
Yeah.
at that point of time, and like small teams with those nice rituals. I remember that 11 a.m. plank thing,
Like,
like
yes.
yeah. But then how the team grew, how
Yeah.
like and how the products actually evolved, and so much of hard work, like absolutely fun to see a product coming out of nothing, like and the
Right.
team growing to a size. And I hear the team is doing well. The product is also landing nicely. I don't think we can
Yes.
talk more about it,
True. We
but yeah.
cannot talk here.
But
Yes. But they
then
are doing good.
it's yeah, they're doing good. So nice to see that whole thing coming together. Um, but in as about like maybe 2.5 years stint in Google, I got this very interesting scenario to work with someone that I knew, who was getting into sort of bringing up this company, getting the funding, and very early stage. Looked very exciting. So that's how I sort of joined the MIPS campaign, and
Right.
it's been a very fulfilling thing. The kind of problem. So we are essentially a CPU IP company.
Correct.
and getting into more stuff which I can talk now. Maybe I can give an update after a couple of months. A lot of exciting things happening. So as of now, it's CPU IP. So we have a core that we have recently taken to production, P8700,
Nice.
with one of the leading automobile customers. Actually, it's in public, so it's Mobileye. Like they've taken that core, and it's a nice four-way out of order core. So decently complicated, and runs Linux and the entire ADAS application that they have. So we give them a cluster of cores, and that's what they use in their solution. So it's and now with that success, we're doing a few more cores, like something that we have recently announced, our microcontroller core for very specific applications with acceleration for very specific end applications relevant for EVs and for power delivery in EVs, and as well as motor control. So that's fun, like seeing the company come together, seeing the company grow again. We were about 30 odd engineers here in India.
Wow.
Now we are 80. So this is
Wow.
RTL, DV, and software, and we are growing. So yeah, so coming to the point, if you're a CPU enthusiast, RISC-V CPU, and you want to explore, how such a machine is built, and how does it get integrated into SoCs, how do the customers take it, so all the way from RTL development to design verification to performance testing of a CPU, or performance evaluation of a CPU, modeling to software, FPGA. So this is the spectrum of activities. We're very happy to talk to anyone who's enthusiastic about it. Yeah, that's my pitch. The culture is, we're a young org, and uh, it's more biased towards action at
Okay.
times,
Right. Right.
as young orgs
Do.
tend to do.
Yes.
So yes, so it's a lot of actions, a lot of quick decision making, and we work in a little bit of ambiguity and entropy. But yeah, that's with each product we are sort of trying to sort of make that manageable and reasonable. But yeah, there's a lot happening.
Makes sense. If I were to put it this way, tell me how accurate or how much of the mark I'm missing. So would it be fair to say that it's like an organized chaos where the general direction is that of get a productive thing out and own it up?
Absolutely. Yes. And what I would add to that is that this chaos exists in all organizations.
Fair. Yeah.
It's just that when you're small and you're young in your, org curve, many people get exposed to that.
Yeah.
Well, if you're big and structured, not many people get exposed to that
Right.
uniformly.
Right.
Some set of people who are making product decisions would, because you make these choices very rapidly. But in a smaller early stage business kind of scenarios, you need to sort of put the reality, like, okay, we were doing this, but then this is
Correct.
the customer feedback we are getting, and you need to sort of course correct or change very rapidly there.
Correct. So more like try things out very rapidly, fail fast, succeed sooner,
Absolutely.
and don't be afraid to take risks. Then last moment changes in things can happen, and I'm imagining much like the earlier days of the team that we were working at Google.
Yeah.
It's like there is so much to decide, and there is very few pointers. We
You don't have a
already know
template. You don't have a template. You don't have
exactly.
something to lean on.
Yeah.
And you're right. Like we were the small team in a large org, but then
Yes.
in our own way, we were like a startup in that.
Yes.
We were
Yes.
just building over. We were taking those decisions. We did not know. Like, it's like throwing a spaghetti strand on the wall, whether it's going to stick or not. So you would
Yes.
do that, and unless you do that, you wouldn't know whether it's cooked or not. So you had
Exactly.
to.
Exactly.
Yeah.
Exactly. And in some sense, I'm also thinking that people who like that level of uncertainty, where their inputs can be tried, they have full control of that situation. Also, it's like what the. I would say it's like, well, again, hard to put it in words, but you as a junior engineer, imagining like somebody at the junior level have that freedom of contributing ideas, trying out things, taking up
Yeah.
ownership, and you're rewarded for that.
Yes.
It's not like, hey, here's your set of responsibilities and the criteria we'll judge you by. Okay, go check. We'll see you after a year, and then
No, yeah, that's absolutely
it's
like,
very
and
dynamic.
that's nicely going back in like to those days in 2021. We were still like, this was still COVID days, so we were working
Yeah.
from home. Yeah, so like there was so much to explore, right? Like, and
Yes.
you wouldn't know whether this is the right thing, or you just did
Yeah.
that and figured out. Yeah.
Yeah. Cool, very cool. So here's the thing. I have now like two, what do you say, paths that I would like to go down. The first one is I slightly want to explore your journey through the field. So we talked about like the companies you worked at, but then could you also talk about what things helped you? Because when I talk to a lot of, let's say, young engineers, well, I'm one of them obviously, but younger than me. So so when I talk to them, one of the things is that the field is very disorienting in terms of the information. Right? You need to know a lot more to be able to do meaningful contributions. So what are the things that helped you orient yourself? What made you feel that, hey, this is the field that I can actually contribute to? Because in the past we have had an example where we hired software engineers, few of them, even the mathematics and scientific computing guys stayed around in embedded, and then few of them ECE they left for cloud computing.
Yeah,
So
yeah, I remember that. No, that's a very, I think, interesting question. Like, it's let me just answer that in two parts. The first one is that, before I go to my journey, that the first one is that, look, embedded software, every 5 to 6 years, it goes through a change. The kind of devices that you work on, that's changing or has changed rapidly. Now, if I look at from my vantage point, from 1998 to now, the complexity of the devices has kind of like evolved like dramatically. The way you debug, the way you the important point is that embedded software always has been a cross-functional sort of a domain. Like, you can't escape the fact that you're really close to the hardware,
right.
and especially the development life cycles in a lot of projects are such that the hardware is also coming up along with software. So you can't expect a pristine environment where things will just work as you want. Like, you will have very nascent, very raw hardware sometimes to work with, and sometimes you would spend days and days on really understanding that, why is my stack getting corrupted, why is my memory integrity letting me down. These are things that you would take for granted in larger systems, right? Like, you
Right. Right.
so effectively it's a cross functional thing. So now, coming back to my journey, um, what has helped me, and not just me, what I've seen people who have not only succeeded, success has many dimensions to it, but what
Right.
I've seen them really having fun in what they do is when, as embedded software engineers, um, they've developed a streak of being curious.
Hmm.
You really want to understand, what's your platform, what are you working on, what is the process. I don't mean process in a very boring bland way, but am I doing pre-silicon, am I
Right.
working on a model, am I going to then work on early RTL in a simulation, am I going to work on an FPGA or an emulator, what are the limitations of that, what can I take for granted, what I cannot, exactly how the hardware is stitched. um, and that curiosity, that time that you need to give yourself to understand what you're working on, that patience and that curiosity, a combination of that, if you do that, that allows you to do your work and gives you this very interesting feel of how to debug a system. So, coming to the point, like, the crucial thing for any embedded software professional is to, especially in the early stages of their career, is to build a knack for debugging. And it
Hmm.
has to get to a point where debugging is something that you start enjoying versus not looking at something that frustrates you, or like it's something that you look forward to. You it's a puzzle that you want to solve. It's a puzzle which is like has cross functional elements you need to solve. So you need to understand your environment, you need to understand what you're working with. And then when you start enjoying it and when you start solving those problems, it just one step leads to the other. Because the next
Right.
evolution, at least for me, and I've seen that very commonly, is that once you get good at it or once you start enjoying it, then you start working with your hardware counterparts and suggesting, when you build the next system, could you please do it this way? Because it makes it more manageable, makes it more scalable, more debuggable. And that's when you start understanding some of the end applications as well. And then your contributions go more than just software. And I've seen many careers evolving. People have started with software, become architects, and they can visualize the system, they can visualize how to make a more efficient system, more scalable system, more reliable system. More debuggable system is actually a more reliable system, more robust system. So
Right.
that's the journey. And the key thing is be curious, be patient, and embrace the fact that it's not a linear progression. It's something that you invest and you get, because it helps you to debug it, it helps you to own the system, become one with the system as you go along.
Right. So if I were to, let's say, press you a little further on this, so let's say someone who is straight up out of college right now, considering embedded as, one of the areas to jump in, and let's say they are hyper curious. So now, what are the basic skills you would expect of them so that they can at least parachute into any of the teams and at least be useful to some degree? Because what I'm imagining is, I'll just go ahead and complete, which is there is one where someone needs like a coaching or some sort of a mentorship, and then over time they figure out what needs to be done. Or there are these people who are curious, have those basic set of, let's say, skills, who can straight up parachute, and then working with them is even more fun because they understand your vocabulary, you would like to mentor them further. So what are those skills? And
So I think it's very situational, but like what you folks are doing and what I've seen of your work, like it's amazing. Like I think that's the kind of thing that anyone who's coming out of like a freshly minted grad, coming out of school, and they want to work in this, or they're making up their mind if they want to work, and they want to give it some time and
fair.
then see.
Yeah.
I think you put together this entire schematic of what they can do.
Yeah.
Because as you very well realize, it's not a single thing that you do and you say that I'm good. Starting
Yeah.
with, what is a CPU? How do you program a CPU? What are the different tools available to you to explore CPU? Like,
CPU.
and
Yeah.
and
Yeah.
and then what does it mean? How does life go beyond the CPU? How do things get interface to the CPU? How do
Right.
you sort of explore those peripherals, the interfaces, and of course the language in which you need to express the logic. Let's take the
Right.
case of C, for example. How can you have fun with that? How could you sort of start working through it, like that complicated pointer which you study in theory? How
Yeah.
beautiful a concept it is when you're working with low level hardware.
Yes.
and and
Yes.
and what does it allow you to do? Like, how do you manipulate hardware over there? How do you then, once you start understanding the peripherals, you start understanding that how does, let's say, a, a serial communication peripheral, how is it going to work? Like the whole serial to parallel conversion, the five fours, the interrupts. Like you got this whole thing. Like, this is like step by step you understand this, build a system, start working with it. That's one way to go. And probably like the work that you guys have done sort of makes it easier for someone to explore. Without that, the only option was that hopefully you've landed up at a good place.
Right.
There are people around you whom you can talk to, and there's a system that you can explore. So you fall, you get up, you fall, you get up, until you start becoming comfortable with it. And what you've
Right.
done is that you've created this nice repertoire bouquet of things.
Right.
Like, these are things like, once you intuitively start feeling them, understanding them, just tell you that this domain is like, this is the start, but then from here it just goes like.
Right, right. At least that's the hope we're trying to kind of arm those curious with that tool set of imagination, so that at
Yeah,
least they can have meaningful conversation with seniors, and then
absolutely.
seniors don't feel pained by having, because that's
Yeah.
another thing, right? In what I've noticed is that like, okay, because the systems are not easy to debug, right? You have like a window through, let's say, JTAG sometimes, and sometimes not even that. You're just like, running tests back to back, hoping that the cache reads the same value as what you intend to write to the memory, things of those nature. But then it's very well understandable that the seniors are constantly dealing with a system that they cannot see, like they don't have visibility into to a good degree.
Hmm.
And then that line of thought is constantly broken by someone, on the side saying, hey, can you answer this one question of mine? uh, so what I'm trying to come at is, if that junior is empowered with tools of imagination, the chances of them having a productive conversation and actually ending up helping the senior are higher. And then that with the senior is happy to have them around, and so it becomes
Oh
like a
yeah,
teamwork.
I think that that's absolutely a important point because finally, you mentioned asking a question and then interrupting the thought. Many a times the person is not even able to ask the question.
Yes, that is true.
That's probably a
Yeah,
lot more painful,
yeah,
right? Like it's
yeah,
so what you guys are doing and that particular format at least gives the person a vocabulary
yeah, yeah.
and a framework to at least ask a question, be curious. And I think that's absolutely important because that gives you the confidence to participate.
Right, right. Yeah, at least that's the hope. And thank you for calling that out. Uh, One other thing, then, the second part that I wanted to go down, which was, could you talk about what are the different teams back in your organization now, and how do they, work with each other? Because there
Yeah.
are folks who see hardware as a separate thing, then software as a separate thing. Could you paint the details of that picture again,
Yeah.
within the bounds of legality? uh,
Yeah, I'll generalize that. So, and it happens to different degrees in different organizations, and it changes. Like it was very different, let's say in late 90s, early 2000s, and
right,
as systems are becoming more complicated, you have a lot more specialization sort of creeping in.
right.
But the simple facts are like, and typically this is on a rainy day, the day you're debugging, that's when things don't work. You see more serious scenarios like this. But even before going there, when you're conceptualizing a new system, and you let's say conceptualizing a new SoC, and that's when the cross-functional team comes together, the
Yeah.
hardware folks come together, the software folks come together, and you start deciding that this is the chassis I want. This is what the product requirements is. So I'm going to have these peripherals. I'm going to have a NOC. I'm going to have a processor. How much of memory do you want? Like all those things come together, and then you start saying that okay, this is what I recommend, and you start building different frameworks for debug. That okay, when I have to test things, when I have to evaluate things, this is how I would go about. That's when the teams come together. But now going back to your question, so typically, and I'll take the SoC kind of a scenario. When you're using a SoC and building an embedded system, it gets a little
Right.
different. But let's sort of stick with this, and we can extrapolate it to that. So when you're building the SoC, typically the whole process starts with a product team coming and conceptualizing that this is the SoC I want, this is the end application,
Right.
and they would definitely give some constraints like this is the area I want for the SoC, it should not exceed this so that I can build it in a certain cost structure. And then this is the power envelope of the SoC. It depends on what kind of an application, whether it's going in a battery powered device or a line power device. So those things change. And then there would be very special scenarios. If there's an SoC going in an automotive kind of an application, you need functional safety. So bottom line, there's this team which does the product definition, and they sort of conceptualize the product. Then typically there would be a few folks who are more savvy with architecture definition and all. They will come in, and they will start defining the hardware and what software goes along with it. Post this, in a SoC scenario, the hardware stream sort of gets sort of split into these things. Like you will have RTL developers. These are folks who will actually develop the RTLs. If they're developing an IP, it's grounds up. If they are getting a bunch of IPs and they need to build the SoC, they will stitch these IPs. So they sort of do the RTL. Then they have their design verification counterparts who will verify the design. These two teams are like tied at the hip. They work very closely together. They also challenge each other a lot more. Like, like they would read the same spec and do go about their job. And when both the teams come together, when the RTL is delivered to them and they verify, it's a very interesting scenario that have both the teams interpreted the same spec in the same way or differently,
Right.
and
Right.
that's where very interesting things can come out. So RTL design verification, this is what we typically call the front end of the hardware development. And then you've got DFT and physical design. At DFT straddles both, but physical design would be what we traditionally call back end. Typically physical design would be two parts: the timing analysis, because you're
Right.
building the circuit,
Right.
someone is going to synthesize it, then does it meet your timing goals and
Signals and
timing conversion
timing
part
requirement.
of it.
Yeah.
And then you've got a bunch of folks, doing the sign off, like, design rule checks. And once you sort of convert the circuit to different masks, different basically layers of the circuit that you'll be releasing to the fab to manufacture for you. So this is the flow. PD team typically would work with the front end team when they synthesize, they do the timing analysis. They will go back to the front end team that, look, you're conceptualizing something which cannot be physically synthesized.
Right.
So
Right.
then they impact the design in that way. So they come up early in the life cycle sometimes and they give this kind of feedback to RTL. But bottom line, PD team is the one which generates the database, which goes to the
The
fab
fab.
for manufacturing, for the wafers and then the devices.
Actually, right.
Software, in parallel, the software team would, like, before going to software, maybe there's very important, like, you will have some other teams which will start working on taking the RTL, which is getting developed, and start building some sort of models, like whether it's on FPGA or emulation,
Right.
sometimes even functional, like on Himu or one of these platforms, like, or Synopsys, Imperis kind of platforms, much earlier, so that the software team can come into place. The functional models are like they functionally sort of map to the hardware being built, but behaviorally they don't have,
They
that
spoof
sort
the
of, yeah,
behavior.
yeah.
Yeah.
So the software teams will typically have people who would do very basic stuff, like the low-level hardware abstraction part of it, get the header files in order, get the memory maps in order, get the build system, and start building the drivers. Take a
Right.
bare metal framework and work with the drivers so that you have some sort of a very, very simple code base
Rudimentary
with which you can
software. Yeah.
challenge the SoC, you can test the SoC. Then you would typically have an targeted OS that you want to run. Let's say it's Linux. Then you will have a different team which will probably use these low level drivers as a reference, but use the driver model that Linux prescribes. Take a fork from a Linux distribution and start building the kernel from there, or
Right.
putting the kernel on the system. The whole idea is that by the time you tape out the device, by the time the PD team handovers the database, the software team has used whatever pre-silicon platforms are available to
Become
reach a
ready.
point where they
Right.
can say this design, when it comes back from the fab, is going to boot. It's going
Right.
to,
Right.
this is where the boot ROM and all those things come up. That code, it's going to boot. It's going to say hello world. It's
Right.
going to, so that assurance is very important, because typically a fab cycle would be a quarter, 2 months to a quarter,
Right. Right.
and you spend a lot of money. You don't want a scenario that it comes and it's not
Oops.
usable. All this is towards that.
Right. Right.
And
So no, go ahead. Go ahead. Complete the story. Yes.
so this is essentially a very Strawman's model. So you have hardware, RTL, DV, DFT, physical design, and then you've got this team which builds the model, also
Right.
does FPGA verification and all, and then you've got the software folks starting from bare metal,
The bare
simple
metal
drivers, to the
upwards.
OS and drivers, and sometimes actually the end application also to a certain extent.
Right. 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 And then now I'm understanding that MIPS Even though MIPS was once upon a time an architecture, still is. But could you talk about this very interesting move of MIPS investing into RISC-V, and then
Yeah.
about RISC-V in general?
So MIPS has gone through different incarnations. So at the early part of the century, it was one of the I guess the four main instruction set architectures if you count
Hmm.
x86,
Hmm.
PowerPC, and
And
MIPS. So
MIPS.
it had its very interesting niche in a lot of networking gear kind of thing,
I
Hmm.
see.
customer premise equipment, gaming consoles, and so on and so
Hmm.
forth.
Hmm.
Then it went through different acquisitions and so on and so forth. And the last scenario was that it came out of imagination, was picked up
Hmm.
by a private entity, and that was the time RISC-V was making a really interesting noise. And what we found was that at that point of time, that pivoting to RISC-V gives us a broader reach. And that was a bet we took, and it was a good bet we took because RISC-V today
Hmm.
is in the embedded course kind of a thing
Right.
is like the examples I
Hmm.
will
Yeah.
like you see that they're finding a lot more use in the embedded course. Maybe not the course where you're running
The
Android
application,
Yeah.
or
right?
but
The
the other course,
microcontroller class. Yeah.
microcontrollers and the cores that feed massive amount of data to, let's say, AI accelerators. And
Ah, right.
Hmm.
Right.
so the beauty of RISC-V is that it's the ISA is open, and then you can
Hmm.
add custom instructions to it.
Hmm.
And what I'm finding is that the whole ecosystem is very interesting. So you can do a scalar core, which is
Hmm.
standard, and you can add some custom instructions. You can bring in some sort of inline
Hmm.
acceleration, and then
Right.
you've got this standard vector unit also that you can add to this. And any of these new applications, like if you're building a ML inferencing engine or so
Hmm.
on and
Hmm.
so forth,
Hmm.
it's a very interesting combination that you can do. And the direction it's going in with the matrix extensions and so on and so
Hmm.
forth,
Hmm. Hmm.
you can build really, really relevant machines all the way from a scalar vector to matrix
Wow.
accelerate,
Right.
Hmm.
Tensor
linear
accelerators. Right.
algebra, tensor
Right.
map, and all that. You could do that in a single processing element,
Right.
in a single pipeline, and then you can replicate this many times over to make a nice cluster of it to do like increase the tops that you
Hmm.
need in your application. So it's very beautiful, and the beauty of this I realized was with you know when you're building, let's say I take the example of AI stack, like a
Hmm.
lot of effort goes in this low level kernel libraries. And like
Hmm.
with this
Hmm.
kind of a pipeline, you could lower your graphs using standard compilers, standard LLVM
Hmm.
Hmm.
compilers. And then you can start depending on the intermediate representation of some of these compiler stacks. It just takes
Ah, right.
the black magic out of the whole thing. It makes it much more elegant, so you can work with
Right.
very new models. So bottom line, RISC-V, the reach made us do this. And as we got more into it, what we realized was that it just allows you to do things that you can do with the traditional closed
Hmm.
ISA
Hmm.
kind of
Hmm.
Nice. Yes.
architectures. It gives you, as we call it, like the freedom to innovate.
Right.
You don't
Right.
have to jump through hoops to innovate. You just have to think through your problem, and
Hmm.
Right.
the RISC-V solution could be very elegant for you, as the example I gave you for the AI part of it.
So, I just want to reiterate for our audience, which is if you want to do the same thing with ARM, you have to jump through, okay, get a license, which I think is 18 months worth of lawyers talking back and forth. Once you get the license, then your engineers need to first understand their RTL, then, go about changing the RTL to add your own instructions.
You can do
Then
that in ARM.
you can, yeah, that's what I'm saying. You can, accept,
You
there's
can't
like,
actually. You
oh,
can't
you
unless
can't.
you
Okay.
you can't break the instruction. So you're locked actually. What you can
Hmm.
do is you can implement your own. If you get
Right.
the
Yeah,
architecture
that's the
licenses, you have to
architecture.
stick to that instruction
Hmm.
set.
Hmm.
No, sorry,
So
I did not catch this. So you're saying there is no space for vendors to implement their own instructions
In ARM,
until
no.
no.
Yeah.
Okay.
I think they have reserved some opcodes, but it's only possible when you just get the architectural license and develop the micro architecture
Yeah, and
yourself.
that's very costly,
That's
and they have the
And
limitations
risky.
there also.
hmm.
Yeah. So,
Okay.
so the beauty. So what do you do with ARM? Like, let's say you want to build a SoC for doing radar processing, which is signal processing. Like you do like three-dimensional FFT. You do with ARM, you would need to sort of build an hardware accelerator. Now, whether you loosely couple it or tightly couple it, you put it on your
Hmm.
fabric, whatever you do it that way.
Right.
With RISC-V, you can make RISC-V itself the accelerator.
Right.
It's your standard scaler. You can add inline acceleration,
Right.
and you can do the same job.
Hmm.
So
Now,
the
So
go ahead. Go ahead.
Uh,
Continue.
I think, Manu, would it be right to say that if I have, something based out of RISC-V, I'm basically setting myself apart from my competitors in the sense that if all of us are using ARM cores, there is only so much we can do. Like,
I don't look at it
Well,
that way.
at least the cost advantage would be there, right? With respect to an ARM IP, you
hmm,
have to like put a price on them in a way that you also get to pay the royalty to ARM. But with
Yeah.
respect to
So all,
RISC-V, you
all
can lower the cost.
all that is there. So both Piyush and Mehmet, like the better way of thinking about this problem is not to think about the licensing cost or the better way to look at this is that you as an architect, if you have a problem to solve
hmm,
with ARM, you're stifled.
Right.
B, even if you even if you could do something about it, you then have to add acceleration, and that's
hmm,
going to eat into your SoC area. You
Space.
start,
Yeah.
hmm,
and in some
Power
cases, it's
also.
going to have a power penalty also.
Yeah. Yeah.
ah,
Now, what you do with RISC-V is that it gives you an open ISA,
hmm,
so you can choose the implementation. You can do your own
hmm,
implementation at times, or you can license an implementation. Now, once you do that, you can extend it. You can
Hmm.
extend the
Hmm.
pipeline if you wanted to,
Hmm. Hmm. Hmm.
and you can do a lot of this stuff, like very simple stuff that you would have to otherwise do outside. You can
hmm,
bring it into the core.
Right.
hmm, hmm,
Right.
hmm,
Right. Right.
And the better way to look at this is that when you build SoCs, you don't build a couple of SoCs, right? You build
right.
The
large volume.
large volume of
So if
them.
you
Yeah.
make the right architectural choices, it saves you
Benefits.
money.
Hmm,
But I think many people forget about the fact that the programming model, if it's pipeline, you make the compiler work for you.
Yes.
hmm, hmm, hmm,
A few people, excuse me, there are few people who go through that understanding, they build the compiler, they modify the libraries.
Hmm.
Not every software engineer has to now worry that there's a hardware accelerator outside. I need to
Right.
feed data to
right.
it. Then
Right.
I need to get an
Right.
acknowledgement. I have a throughput problem, or I
Right.
have a
Hmm,
power problem. How do I sort of
hmm,
make them work in some sort of,
Right.
so that's the big, like that
hmm.
elegance of the architecture is what.
So,
That's a very interesting point, actually, because
right.
along with the core development of your RTL, you also need a team which is looking at the tooling to make sure that it fits
Hmm.
nicely and sort of gets the most juice out of the very specific core which I have for my application.
Yes.
Hmm.
Yeah. Now with RISC-V, all that, and again, we can get into specific example, but in the company we have
Hmm.
worked together, like
Hmm.
there are teams which have used this to a point where uh, very complicated and essential blocks in the system have become very elegant in terms of programming
Hmm.
because
Hmm.
you've
You now
used a
have
RISC-V
a
pipeline.
right, and to simplify this, you just have like one instruction that can get the job done for you. Versus, if you
Hmm.
have an accelerator, you first have to target the memory mapped IOs
Right.
or
Basically, a
Sure
registers,
thing, again, yeah.
all of
driver
that.
gets replaced by just one instrument. That's it.
Right.
Yeah.
My
Yeah, this
follow
becomes
up.
a driverless
Right.
kind of a model.
Kind of.
Yes. So it's like your normal
Excuse me, guys,
program.
can I grab some water
Sure.
if
Sure.
that's okay?
Sure.
Absolutely. Yeah. Yeah. No worries.
I'll just switch off my camera for just 1 minute.
That's a very interesting.
Yes. Very, very cool, actually. So instead of having like a
I'm now thinking more on the tool chain because that has to be so smart.
that is going to be my
Hmm.
next question, which is okay. We'll let Manav be back.
Hmm.
I'm thinking he can still hear us.
Hmm.
Which is, if let's say I as an architect add certain opcodes in the
Hmm.
vendor opcode region,
Hmm.
who writes the compiler related modifications, and
I
then
suppose
how
it has to be the same organization, because then the
it
idea
has
is
to
that
be,
it
yeah.
has to be. Yeah.
So there needs to, hopefully there needs to be like a team who now know that there are these new
Mm.
instructions that needs to be kind of passed by, let's
Right.
say, the assembler
Right.
or the
So
compiler.
even the addition of these hardware blocks or new instructions, so to speak, has to be thought through all the way to software. Like, hey, this is the software, and this is where I'm gonna
Yep.
replace these. I think Manu is speaking. Or
Uh, can't hear you, Manav, in case you're talking. We'll just wait for him to come
Hmm.
back.
So,
We'll just look at the on the screen. Yes,
yes.
you are. Okay, now you're not. Okay. Okay, I think Manav dropped off. Hopefully he returns back.
Mhm.
But yeah, I'm also thinking that there have there has to be a team which takes a look at, okay, these are
Definitely.
the new instructions and we must add it into like the
Yeah. So you
compiler.
can, I suppose you can start off with very simple addition as like, just a switch case where you just take, hey, this instruction, I need to, sort of map it to these opcodes, and that's it. And then your, uh, you know, evolution can begin, sort of like where compiler becomes smarter.
Yeah, I think Manav's back.
Yeah.
I I came back. My session has to restart.
Oh, okay.
Hmm.
Perfect. But you're back now, so that we both were in the meantime talking about the fact that, let's say, an architect has implemented new instructions, and to the new instructions there is like an internal hardware block mapped right within the RISC-V core now. So definitely there has to be a team which takes a look at those instructions and then modifies the compiler
Yeah, and you can do it in multiple ways.
Hmm.
You could contribute it back if you want them to be
to
open.
the
You can
community.
contribute it
Yeah.
back, so you can use one of the LLVM or GCC brand, or you can
Hmm.
work with intrinsic. So that's and you can then target the
Mm,
library that which is using those. Let's
Right.
say you add something which happens to be in the math library, particular. Let's say you are
Hmm.
right.
an alternate function for um, uh, finding the codec more easily rather than
Hmm.
doing the
Hmm.
entire Taylor
Hmm.
series
Hmm.
truncation. So you could add a instruction and do that,
Hmm.
and then add it in as with the intrinsic
Hmm.
in the math library itself, an alternate way to
Hmm.
do it. So you don't need to sort of write the entire compiler then.
Hmm. Hmm.
Makes sense. Makes sense. And just to get more clarity, let's say new instructions are added, and the compiler folks have taken care of it. Whether or not they contribute to the community back, let's leave that for a while. But then, do the compiler changes have to be smart enough to figure out like a pattern in the C program? Like, let's say you have
Hmm.
three for loops, and then it's like, okay, this might be like a convolution operation,
That's why
something like
Piyush,
that.
most of those constructs are taken care of by the standard instructions. It's a very rich instruction set. Okay, the
I see.
standard.
Okay, I
But
see.
what happens is think about it that you have a call for an FFT function, for example,
Fair.
which
Yeah.
is very specific. And when you call that FFT function, the control goes to a library,
Hmm.
which is
I
meant
see.
for sort of
Okay.
that's where you sort of
Right.
intersect that. That's where you redirect it.
Hmm.
I see. I
So
understand.
basically, we are cutting the entire compiler layer. It's just that assembler has to just like
Yes.
insert the
So
opcode.
correct. So I was going to then say the library that Manu is referring to is actually written in assembly
It
for
could
or
be in
or a
assembler.
C as
C.
well. It can be C
So
as well.
ASM instructions with
But
You could just yeah
okay, you can
hmm,
add the assembly
intrinsic.
instructions within C.
Yeah.
Fair, fair, fair. Well, I was going to mention that, okay, there is like a implementation in assembly, which is kind of aligned with the ABI standards. So you can call that as a function from
You could do
C,
that as well. You
something
could do
like
that
that.
as well. Yeah.
Right.
The multiple
Very cool.
recipes. Once you
Hmm.
basically
Fair.
what you do is you identify a job that you want to do more efficiently,
Hmm. Hmm.
and then but the basic structure of your conditional constructs, your looping, and all
Hmm.
that's taken care of by the regular stock instructions,
Right.
which are
Right.
very
Right.
rich.
One of the things I want to call out is one reason why people would want to do this, like introduce their own instruction instead of going like mapping the IO mapped memory thing and having registers to program an IP, uh, is it has to do with the thermal threshold, right? Like given a computation, let's say AI workload, it consumes certain amount of power, and what we are trying to do is reduce that power.
That's one of the side effects of it because you're not making that particular computation happen far away. You're not going through a very dense
Hmm.
knock or a fabric and taking it. So that's one. But I want to sort of give one more point. Like it's not just these custom instruction or the fact is that the openness of it. There is a
Right.
huge community contributing to it. It's I was like completely amazed by the richness of contributions which are coming on the like whether it's the LLVM project or the
Hmm.
GCC project or libraries. It's so
Mm-hmm.
much now. You could add more, you can do more, but there's a lot happening around. And
So, would you say, Manav, that there has been a surprising backflow of things which could have been proprietary, but people chose to contribute it back to the architecture,
yes, that's there.
just like Linux?
People, yes, it's a
Hmm.
very similar phenomena in some
Hmm.
sense, and that's why it's finding more and more use. It started with
Hmm.
simple embedded CPUs, but then it's finding some niches like the AI
Mm-hmm.
one that I mentioned. It's becoming extremely popular to look at this
Hmm.
machine in a like you scalar and the VPU coming in the same this thing, so you're not going by that
Right. Right.
very uninteresting neon kind of.
Hmm.
It's
Mm-hmm.
pretty
Hmm.
elegant, and then you add a matmul and make the entire
Right.
system in a very simple, elegant way.
So we
Well,
started all the way from like completely application specific ICs, and then this boom of generic processors came where software could do a lot many things with a generic piece of SoC. And then now there is this hybrid of there is something generic, but then
Yeah,
you have like this very nice framework to
specialized,
put
yeah.
in your specific stuff and
yeah.
get the most out of
Yeah,
it. It's
that's
interesting.
the very interesting economics
Hmm.
of the industry. Like you always see this cyclical thing happening.
Yeah.
You come up with specific this thing. Like think
Right.
about the DSPs and the modems, right?
Hmm.
Like
Yeah.
then you wanted because the cost became a factor. You wanted more and more modems at lower
Hmm.
and lower prices. You started sort of doing them in a very like in a sea of gates, build more and more things and so you go through, make it more specific. Like you take out the openness and be very specific. Then the
Right.
next thing comes, which is so complicated. You again do it in a
Right. Right.
very broad manner, and then they
Hmm.
come.
So these are like iterations over decades.
Hmm.
Yeah,
I
yeah, it's a very interesting trend. I've seen it in so many
Right.
different end applications. It's very fascinating to see how
Right.
the whole economics of that particular
Hmm.
sector sort of takes over.
Right. I just want to stretch the RISC-V topic a little bit more, which is so in their earlier presentations, the sci-fi folks, again, Yoon Sup Lee and I forget the professor's name right now, but
Krista,
David
yes,
Patterson?
no,
No,
no, Krista.
Chris.
yes, that. So So they mentioned that they started off with the embedded course, and again, RISC-V has like this multiple layers to it, right? The machine mode, hypervisor mode,
Yeah,
supervisor, and the user mode. And I think if they have the machine mode and user mode, or just the machine mode, it's an embedded core. So they started there, and their intention was that first they'll take over like the microcontroller market,
or
the
embedded.
tiny
Like
cores.
you have very simple jelly bean
Fair.
cores, sort of.
Right,
Yeah,
simple state machines written in
yeah.
firmware, that kind of market, and then slowly they'll evolve towards like going generic to the point that there is an application grade and even server grade,
Yeah.
architect. So with respect to that, where do you think RISC-V is now, given that you're actively
No, I
looking at
think
it?
they RISC-V. If you take the specific scenario with sci-fi, they took their own decisions based
Right.
on, like, any engineering team will have a certain bandwidth you need to focus. And but
True.
going to the generic RISC-V standard, they've had different profiles. What you were just
True.
talking about was different
Hmm.
profiles. So you can
Fair.
have a H mode, so the profile with the hypervisor, or without that, or a very simple sort of a scenario, like 32-bit profile, 64-bit profile. So they have these profiles. Now, given that it's a very contemporary instruction set, it and the way this whole RISC-V international process works, it takes a lot of inputs, and the scope for disintegration is reduced so much that, so they have factored that these profiles would exist,
Hmm.
and and so you could choose, if you were a RISC-V IP entity, you could choose that which profile do you want to start with, or what's your need.
But then, based on like your visibility now, do you see other players going in the direction of like application grade CPUs or
Oh
server
yeah,
grade
yeah,
CPUs? So
yeah,
they are
yeah.
okay.
So it's
Interesting.
it's becoming fairly common for folks to do an out of order machine.
Hmm.
The reason you would do an out of order machine is that it's going to get into something more, dense, something more demanding.
Hmm.
In
You you
terms
you
of
want
Hmm.
compute.
more out of each clock edge, kind
Right.
of.
So you're basing that data point as a sort of a guide towards saying that more and more
Yeah.
applications are found in the compute cores basically.
Yeah.
Right. Okay, so I now want to combine together RISC-V and automotive. So we talked about the fact that there are RISC-V solutions being deployed to an automotive, and then somewhere there was ADAS involved. So my question then is, well, first thing is there is hardware innovation, right? That
Mm.
RISC-V enables, and then eventually it translates into like the speed and the power. So on an automobile, I could argue that maybe we don't care about power as much because the vehicle, the
That,
engine is
that's
there.
that's
Yeah,
not that's not
not
true.
true.
They do
Okay,
care about power. They do
fair.
care about the predictability of power. So if you
Okay.
Ah.
and I'm sorry about interrupting here, but just a
No,
quick this
go
thing.
ahead.
So typically, ADAS module, or whether it's vision or radar, these are in hermetically sealed boxes when they get installed
Hmm.
in your car. So the
Oh,
electronics in that, you have very specific thermal resistivity sort
right.
of requirements. So you burn power, so that's your in that environment where there's probably no airflow, the
Right.
gradient between the ambient temperature and the junction temperature could be much larger.
Right.
So you so you
Have
would
to care
want
about
to
that. Yeah, yeah, yeah.
keep the junction temperature, hence the power consumption. But
Hmm.
again, you're right. You're saying that it's not a battery application. That also
Hmm.
sometimes is
Ha.
not true. In a car, like if you're on the battery grid, certain applications like your key fobs, your door detection, and all that
Security. Yeah,
happens
yeah.
in a completely. It's not on the ignition bus, if I may.
Hmm.
Fair,
So
fair. And
it's. But anyway, the reason it's interesting for automotive as well, Piyush, is that what we don't realize is that there is a lot of pressure on the semiconductor entities which supply automotive chips to become
right.
as innovative as their, let's say, mobile counterparts, or like others, along with a huge overhead of functional safety and doing
Hmm.
things with a certain process. So there's a lot, and they would want to innovate, but they would want to also get the right return on the investment. So RISC-V is very exciting for them as well.
Hmm.
And there have
Interesting.
been people who have come out of that safe space of using the legacy, and then trying something new,
New.
and trying to see how they can leverage this, how they can sort of build a system which is
Right.
more, which can give them more, and can sort of secure their investments for long term. So they're making this transition. It's sure transition which is happening, and they
Right.
look at the benefit that this gives them.
Fair. So, I'll just correct myself then. So, power and speed both advantages are like very much welcome on the automotive side. Could you speak to the speed part of it? Like, what advantages are there if my core runs slightly faster, or the computation happens slightly faster in terms of
Well,
automotive?
well, it's simple. Like you could do more.
That's one.
As an
Yes.
engineer, I've always, like as a software engineer, embedded software engineer, I've always been in situations where, let's say, one of the devices that I did, we had to
Hmm.
do the entire AGC algorithm of wireless standard in firmware,
And could you
and
expand
it's
AACG?
automate it's automatic gain control. So you
I see.
basically look
Okay.
at some samples, and based on the energy that you see in the samples, you change
Sensitivity.
the low noise amplifier gain so that you can then control, and you keep
Hmm.
on doing this again and again.
Fair.
The thing is, this
Ah.
loop has to run in a certain time,
Hmm.
and over the time you keep on adding more checks. Like there is a bug in the hardware, so you read a register
Hmm.
twice.
Ah.
they so you keep on accumulating. So the faster it is, it just gives you more cycles to play with,
Hmm.
and your product becomes more scalable. Tomorrow you have to
Right.
add something in software, you can do. But in the more
Fair.
contemporary system, it's more like when you're running an OS, when you're running
Hmm.
processes and all, you have more headroom. You're more
Hmm. Hmm.
immune to a
Hmm.
change that you can end up. Otherwise, like you will have to always keep on doing a new hardware when there is any new change in software. So you want that
Fair.
headroom, you want that sense of
Right.
like I have a scalable system.
Okay, so I'm imagining that I just want to paint like a realistic, what do you say, visual, which is, let's say, my car is running at 100 kilometers an hour, and it can do computation at a certain rate, so it can detect objects that are far out and engage the brakes. So if the net computational speed is going up, maybe my car can run fast. I can go till 120 or 140 without compromising the ADAS or the
Yes,
braking system.
that's
Would that be
one. Well, that's one side
eventual?
effect. One good side effect of having more clocks in your hand, more productive clock edges in your hand, because then you could do like maybe I can give you a more practical example. Like with all these EVs coming in,
Right.
the real time control of motors, you want to run the control loop as often
As
as you
fast
can
as
so that
possible.
you can have the motor more responsive and more smoother
Nice.
and all that. So
Nice.
Hmm.
that's a trend they've seen. Like you want to do that computation, those transforms more and
As
more,
fast as possible.
so that you can do it more often
More.
in a
Yeah.
yeah.
So like this, the implementation in software, the loop runs many times in
Yeah,
per unit time. Okay,
yeah.
perfect. Perfect. Wow. Okay, now I want to then full circle go back now backwards. So you're doing things at MIPS, innovation there. Google stuff, I think I'll keep that out because NDA. Then let's go back to TI. What was happening there? Radar
TI was
systems, something.
yeah, you know, like it's a fabulous place. Like the company has, like I just love their motto. Like like making electronics affordable. Bringing in
Right.
electronics, uh, making it accessible by innovation in semiconductors and all. So I think the beauty of TI was that working on the end applications very closely. Like my last project there, I was the R&D manager for the radar business unit. So looking at the product line start from absolutely basic stuff, basic concept, something coming out of the research lab, all the way to a product which is deployed very widely. That sort of a journey, and seeing it very closely was like something exceptional about TI, and that was the sort of company where you could get that visibility even as a young engineer.
Right.
Like you could
Right.
see where the product is going, how it's going to be deployed. So absolutely, like if it's fabulous place to work when you want that visibility, when you want to look at
Right.
that end to
Right.
end sort of a thing. And the kind of applications they've gone after, the kind of shift they made from wireless to automotive, industrial was phenomenal. To see that entire
Hmm.
shift executed was like sheer persistence, clear headedness, and how the whole business was sort of more you know, course cut, change of course, and it was fabulous to see. So TI as an organization, the engineering, the field, the sales, how this whole thing comes together to create value for stakeholders was amazing.
Hmm.
you know, I don't know if it is okay to talk about it here or not, and Mano, you can choose to not answer
Yeah.
it. But I recall, once we were taking like a round around the building, and Mano was talking about a very interesting scenario of. So the idea is that you have the RF waves, reflecting back, and you detecting like a radar system, essentially detecting uh, the environment around the blockers, barriers, and all of that. And then there was an interesting problem that Mano spoke about, which is on the edges of the object, the radar doesn't do as much well, or you have to take care of a lot of things. Could you talk about that at a
Yeah, so
technical?
I mean, I'll put it in the context of how it was interesting to work at TI without getting into the specifics. So the thing is that when you build a product and you build the algorithm and you build the algorithms for it, the software for it, you test it in the lab. You test with perfect reflectors, you test with different scenarios, but when you get to the field, you see scenarios which are very different. So the thing about AI was that an average engineer would be well connected through the sales, field application engineers with what the customer is doing, what kind of checks
Right,
they do.
right.
So you see these scenarios that how do they test in this case, let's say this particular system, and you if you understand, and then you try to solve for it. You solve with the customer. You give them a solution, and in the process, you make your product better, and you learn so that in the next generation you can do something different. So
Improve.
that
Right,
was very interesting. That entire learning from how people are using your product, what sort of issues you can see in the field was
right.
amazing there.
Perfect. I just realized at the start of the call, Mano did mention to us that it was very difficult to make him talk for 1 hour. So that's a win. Okay,
Yeah,
Mohammed, you have a
I
question?
have.
Yeah,
Yeah.
right.
So, Mano, I think you are the one of the perfect ones to be asked this question, and it's a kind of an opinionated one. So maybe I'll look for and seek for your opinion. Is when you started your journey, I think the embedded world around that time was like very less abstracted. Everyone was doing everything, they knew all the layers, they were like working on all the layers, versus the life at this point of a embedded developer. It's like fully abstracted. You just get to look at just one thing and rest all is assumed to be working. So which one would you choose? Like, given a chance, would you
Right.
prefer working in early 90s, let's say, or, right now? And secondly, second part of that would be, let's say if someone prefers to peel the layer of abstractions, what would be your advice? Like, till what depth should one go?
Yeah, my honest answer on the first one, Mehmet, is that nostalgia is an interesting thing, but the fact is that change is every engineering discipline changes, and systems were less complicated.
Hmm.
I always give this very simple example that in my generation, average software engineer would sort of put a zero ohm resistance themselves, but that was
Hmm.
possible because the size of those resistors were like like you could see them, you can hold them with a tweezer, and you
Right.
you could
Plug them in.
solder, and the basic education system also was not that specialized, so you
Hmm.
would come in with some knowledge of whatever, and you would, but I think so there's nothing right or wrong. It's just that as things become more specialized, you would sort of like draw an analogy with the medical profession, right?
Hmm.
Like,
True.
I'm sure 50, 60 years back, there were not so many
Yeah.
specializations. Like,
Fair.
it's very similar to that. Now, as things become more complicated, let's say bringing up a Linux kernel on a pre-silicon scenario is much more difficult than,
Hmm.
let's say, bringing up a bare metal loop on a, in
Hmm.
maybe
True.
25 years back in that kind of hardware. But then the debuggers were very clunky. Like, I remember my first debugger was the size of a suitcase. Like, you in so Nowadays we don't even sort of worry about it, and that was very
Yeah.
unstable as well. Like you sneeze near it, your session would go
Hmm.
corridor. So yeah, so it things have changed. So I think
Right.
one of the things I've learned, again, the white in my beard and my hair, is that to accept the change. It's just
Hmm.
it's constant, and so there's nothing good or bad. But then coming to your
Hmm.
second question, which is I think where the if someone wants to do this, it's possible today as well.
Right.
Hmm.
Now, what you need to do is, and again, I'm not getting into organizations, different organizations can have different boundaries, but I've been blessed that no one has stopped me from exploring. And my guess is that's the case. Like, no one stops you from exploring.
True.
Like, i- it is perfectly okay
Hmm.
if you're working in a pre-silicon environment and you understand a little bit of VHDL or Verilog, just
Right. Right.
understand how the models are coming together. Or if you're working on post silicon on a board or something, really understand how the whole board is
Hmm.
coming together. And but yeah, so it's if you're interested, you could
Hmm.
still do. But I think what's happening is the speed at which you need to deliver nowadays is so much
Yes.
that would you have the time, that and
Yeah.
that becomes a very personal thing, that how much
True.
you would
You're
invest and
investing.
how you would do that.
Hmm.
Because with all these things coming up, the cycles are shrinking.
Sure.
You need to, and people want to do more and more software even when the device is not there, right? Like you want to bring
Hmm.
the entire OS, your application in the pre-silicon scenario. And but point is, if you want to do that, it's still
It's true.
you could do.
I,
But
I think
earlier
it is. It
it
is
was
tying
not.
back to your earlier advice, which was curiosity. So now it's kind of
Yeah.
driven by curiosity rather than
Yeah,
necessity.
so earlier it was like a part of your
Hmm.
job description. I'm sure when people used to write JDs for embedded software folks
Hmm.
at that time, it would be very
Hmm.
different from
Well,
what you see
what they
today.
do
yeah.
now. Yeah, yeah, yeah. And in fact, I would kind of, add saying that, it's a lot easy to get started now. Like you could just get started with QMU and,
Hmm.
Yeah.
on your own
Yeah.
system,
So that's
no
the beauty
upfront
of abstraction,
infrastructure.
right? Like you
Right.
could,
Yeah.
yeah.
Wow. And okay, so I think we can come to the end of the podcast, and I want to ask one final question, like a mandatory one. Uh, how do you think, the tools are going to improve, or like the velocity of execution is going to improve in the embedded space because of AI? Again, like a mandatory question.
I think um, I've started seeing, and when you
Okay.
see some of the engineers, like they are. And when we say AI, right, we sometimes use AI as a proxy for
LLMs.
Gen AI, LLMs
Hmm.
Yeah.
mostly, because that's what we. But it's a
A
lot more.
lot more than
And
that.
we're
Yeah,
again talking the
definitely.
cliched part. So
Yeah.
they use a lot of these platforms for
Hmm.
a very quick check on something. But the most beautiful scenario I've seen is that some really smart kids, they instead of going through the data sheet themselves,
Hmm.
They
they will
feed
give
it
that
through.
to the tool, and then the tool becomes like your personal chatbot. Like,
Right.
okay, uh, what is the register, the interrupt?
For X
I-
function.
Can you just give
Yeah.
me this particular set of bits? Like, if I have to modify this bit, can you give me a macro? And this is my
Hmm.
style of writing the macro. So
Hmm.
those kind of things are
Right.
happening, and I think they're good. They're
Right.
fine. Like people, like why to go through a bland, like in my days, data sheets were not even available in the so you had these
Hmm.
fact books and
Printed.
all that, and you had to go through
True.
and you had to share
True.
them with multiple
Hmm.
people. But then it went to these PDFs
Hmm.
available somewhere on the drive, you pick up and read. Now people are just disintegrating them and just going
Right.
through the stuff that they want to.
Right. So
Hmm.
extracting information is faster.
Yes,
So
extracting information. When you're debugging something, you want a
Right.
quick thing. Like instead of like changing context so many times, you're almost like
yeah.
interacting with a
Hmm.
friend or a mentor and getting that information. And hopefully, it's the right information. The
Hmm.
Yeah.
model is trained properly.
But I think that always stays, right. The information we are consuming, whether from the data sheet or an output of an LLM, needs to be it needs to be tested with the reality
Yeah,
and verified.
and yeah. I think a smart engineer would do that. Like
Yeah.
it's just the instinct you do when you're coding, when you're testing yourself. You do you're cognizant that you're relying on some information and whether
Right.
you've captured it fully or not.
True. Cool. I think with that, at least my set of questions for the day are
Thank you.
done. Yeah,
I'll
Mohammed.
just add this that every time I have talked with Manav, it's I've gotten this very top level view of how industry works, and
Yes,
I'm
same as well.
always gone back with a lot of learning. So thank you so much, Manav. Not just for this
It's a
podcast, but
it's a
for
pleasure, guys. It was fun working with you guys at and at Google, and lovely catching up with you.
yeah,
And let's do this again anytime. Like
definitely.
let's catch up in person
Yeah,
sometime.
I have to
yes.
propose this that next time we catch up, let's talk about the chip wars, the book.
Ah,
Because
yes,
I
yes.
know, Manav has read through that, likes it a lot, and it gives like a perspective on how the semiconductor manufacturing came about,
Hmm.
where it's headed, what are the different stakes of different countries. Yeah, all of that.
Chip
Yeah,
wars. I
Chip
will also
wars,
it
yes.
was. Yeah.
give it a read.
Yes,
Okay.
yes. Perfect. I
Okay.
think I'll go ahead and stop the recording.
Okay.
All
Thank
right.
you so
Thank you
much.
for being with
Yeah.
us, Manav.
Thank you so
Thank you
much.
for
Sure.
giving us your time and making the time for us. Yeah. Thank you.
Take care.